This is an additional resource for 6.2, transforming random variables and combining random variables. So first we're going to look at transformations, which we already looked at before. So if you already remember what addition, subtraction, multiplication do, you might want to fast forward this till you're about halfway through. Because we did cover this earlier, but not with random variables. So remember, a random variable is an event that has a chance process and all the outcomes are listed. So here we have the random variable of how much money you would earn by coming to class. And if you remember, there was a video on this before, and I talked about how you would pull out your wage, and that's what you'd get for the day for attending class. And I just made up these probabilities because I don't have the actual data because I did a different one in each class. So these are just made up from the previous video. All right, so I put that into my calculator, or I could have used the formula on the formula sheet to find the mean and the standard deviation. But remember, I had to weight each value. So I did 1 times 3 over 30 plus 5 times 6 over 30, blah, blah, blah. Summed all those, which found the expected value, or the mean, meaning that if I could randomly draw a wage each day over many, many days, I would expect to get $8.40 per day, with a standard deviation of $4.76. So typically, I'd vary from that $8.40 by $4.76. All right, so what if we already have data like we do, but we decide that we want to now change that data slightly, but everything else stays the same. The proportion stays the same, and the number of outcomes, but we're just adding to each one, right? So all I am doing is changing each individual outcome by adding 10. Okay? So if you put that into your calculator or do the calculations, you're going to find that you're going to get $18.40, which is just the mean plus 10. So adding shifts our entire set of data. Notice it's all lined up like it was before, but we just shifted everything, right? So we just had a shift of 10, so it shifted our mean. Now if we look at the spread, right, 25 minus 1, 35 minus 11, our spread didn't change. And if you were to calculate this, put it into your calculator, you'd find that that is also true. So the spread does not change, the standard deviation does not change, but we shifted our data so the mean obviously increased by 10, right? So how did adding a constant affect the mean? So whatever you add or subtract will shift the mean, right? So we'll add or subtract. It'll affect the mean the same way. Okay, but notice the standard deviation remains constant. So that's what we learned before about adding and subtracting. Now we're going to take a look at multiplying or dividing. So we're going to simply keep the same data, same order, but all we're doing is doubling the outcomes, right? So when we multiply, we're not shifting the data, we're expanding it, right? So as you can see, we went from 11 to 35, 1 to 25, and now we just expanded that, which expanded our spread. So we're going to do 2 times the mean and 2 times the standard deviation. So multiplication does affect the spread because we're expanding the values. So we get 1680. And if you put this into list 1, this into list 2, calculate one variable statistics with list 1 and list 2, you're going to find this. So, I mean, we can take this shortcut, or we can just simply double it, okay? So how does multiplying affect the mean and standard deviation? Well, yep, you can multiply to mean, you can multiply to standard deviation. All right, so that was our first learning target in 6.2. And if you haven't already, try this check your understanding on page 9. Just try to apply what you learned, pause this, and go through it. If you already did it, fast forward, that's fine too. All right, so the scenario we have here is we have all the states in the United States, and then we have all the outcomes of number of billionaires per state. So there's 12% of the states have 0 billionaires, 24% of the states have 1 billionaire, right, as you can see. So here's our scenario right here. The random variable x has a mean of 12.68. So on average, states have about 12.7 billionaires, right, with a standard deviation of 29.02. So as we can see, it's really spread out. Suppose a law is passed requiring each billionaire to pay $1 million to their state. Let y, so we have a new random variable, y be the money received by a randomly selected state. So what we're going to do is we're going to take this original data, right, but we're going to multiply each. So 12% of the states are going to get 0 because 0 times 1 million is 0. 24% of the states are going to get $1 million from that 1 billionaire. So we're going to go through and we're going to multiply by 1 million, right, to every single value. So we don't need to do that and put that into our calculator. That's a lot of numbers to put in when we already have this info, right, and the knowledge that we just reviewed. So first off, consider the graph of the probability distribution of x and a separate graph of the probability distribution of y. How would their shapes compare? And so this is another reminder, the shape doesn't change, right? So there's no mathematical operation that we could do, adding or subtracting, multiplying or dividing a constant, that would change the shape. We need to find the mean of y. So if you remember, the mean can be multiplied, so I'm just going to do 12.68, which was the mean, times 1 million. And I'll get 12,680,000. Okay. All right, so there's our mean. Now we need our standard deviation, which is also affected by multiplication, right? So it expands it, so it's going to be way more spread out. So I'm going to multiply that by 1 million as well, and I'll get 29 million. Okay, so interpreting that, the amount of money received by a randomly selected state would typically vary by about 29.02 million from the mean of 12.68 million. Okay, and then 4, each state agrees to invest 500,000, $500,000, to improve roads. Therefore, the net amount of money a randomly selected state has after the billionaire tax. So the state's going to use this money for a specific purpose. So we multiplied, right, to get y. Now we're going to subtract. So now we need to analyze if we take each, imagine that we created a new random variable where we multiplied each value by 1 million. Now we're going to subtract 500,000 from each one, describe the shape, mean, and standard deviation. Well, the shape is going to stay the same, right? Because subtraction is not going to affect the shape. The mean will get shifted, right? So it'll be 500,000 less, so 12, right? So I just took the original, well, that mean, right, in number 2 and subtracted that because it said take y and minus that. Okay, so standard deviation does not get affected by subtraction, so it's going to stay the same. So we're going to have that 29 million. So we'll still be, when we create this new random variable distribution, it'll look very similar, but it'll still be expanded because we still have that multiplication, right? But it'll also be shifted. All right, so that's what you need to know for the first half of 6.2. Second half of 6.2 is combining probability distribution, so combining random variables. So we're going to go off the same story problem to help us visualize this. So I just put this in my calculator, this data. I put this into list 1, this into list 2, 1 var stats, calculated it with L1 in the X and L2 in the frequency list, and it told me my mean was $11.85. Variance, if you remember, is standard deviation squared, because it's actually, when you're calculating the standard deviation, we're finding the distance from the mean squared, and so this is before you take the square root. That's variance. But you can find it by just squaring your standard deviation. The calculator gave me a standard deviation of 2.22, so I squared that and I got 4.93. So this is the standard deviation, right? Squared, meaning it is the sum of the distance from the mean squared. All right. So we had hourly wage, and then we have hourly raises, and I did the same thing. I calculated the mean was $1.60. The standard deviation was 0.917, so about 92 cents, which made the variance 0.839. Okay. All right, so the scenario says, let N be the hourly wage for the upcoming year. So they're going to get this new hourly wage. 30% are going to get $9, 45% are going to get $12, 25% will get $5, and then they're also going to get a raise. And they might get the $1 raise, and then 30% are going to get the $3 raise. So we need to combine these two scenarios, and we need to find what are the new hourly wages, right? So they could get $9, but don't forget they are going to get a raise of either 10 or 9 plus 13 of 12, right? So they could get the $12, but then they could get a raise of 13, so 12 plus 1, right? Or 12 plus 3 of 15. Or they could get the original $15 an hour, which would give them 16, and then 18. So those are all the possibilities, 10, 12, 13, 15, 16, 18. And then B says, what is the probability of an employee being assigned a $9 wage and a $1 raise? So up here, it said, assume X and Y are independent. So if you have a wage of $12, and we know that, that's not going to affect the probability of your raise. Okay, so they're independent there. So both of those guys are going to happen, 9 and 1. So I'm going to take 0.3, so probability of 9 and 1. They're independent, so it'll just be 0.3 times 0.7, which is 0.21. So we have a 21% chance that we originally get the $9 wage with the $1 raise. So I'm going to finish this table by doing all of those probability of the original and the raise. So like I said, 21, 0.09, 0.315, 0.175. Oops, I missed. Sorry, I already computed these and I wrote it down wrong. 0.135, 0.175, 0.075. Okay, so I found the new mean, which was, and I just put these in my calculator again in list 1 and list 2, and I found that I had $13.45, and the standard deviation was $2.40, and the variance, when I squared $2.40, was $5.76. Okay? Now, D says, if n equals x plus y, complete the following in terms of x plus y. So, if I am adding the means, let's take a look at that. Because we do have, all this data is coming from the same original places, and it's a combination of the two. So let's take a look at that. What happens when I add those? Yep, they equal 13.45. So meaning, hey, you don't have to, I didn't necessarily need to go back and recalculate the mean. I could have just done the mean of x plus the mean of y, and then I would have had the mean of n, right, as you can see there. Okay? All right, so let's look at our standard deviation. If I add those, I am not going to get $2.40. No way, right? Okay, so as we kind of investigated before, you cannot add standard deviation. Addition isn't working with it, okay? But I kind of randomly brought up variance here, right? So why was I bringing up variance? Well, take a look at those. If you add those, you do get $5.76. So it looks like you can add variance. And if you kind of think about the math there, that's before we take the square root, and so something's happening there that's really interesting, but it does work. We can add the variance. So what we need to do is we need to take the variance of x and add it to the variance of y, and we're good to go. But remember, that will find the variance of x plus y, so then we'll need to take the square root. Okay, and if you do that, and I did do it, you take that, square it, take that, well, that is the variance, so it's already squared. So take that, add it to that, take the square root, you'll get $2.40. Okay, now, the book's going to explain this, but I don't have a specific scenario for this. But if for some reason you need to subtract, so what if n was x minus y? Yeah, of course you can subtract those and you'll find your new mean. But the thing is, with variance is the spread. So we are combining, even though we're subtracting, we're still combining the two. And whenever you're combining things, we don't want to cancel out spread. Okay, so because of their combination, the spread will actually stay the same. So if we are subtracting, the second scenario where we're subtracting, even though we're subtracting, we're still going to add the variance because we're not diminishing any of that spread. Whenever we combine, the spread is not going away. Okay? So never, ever, 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 ever subtract variance. Never add standard deviation, right? Only add variance. So let's take a look at some check your understanding here. Okay, so we're still adding, so we don't have to worry about the stuff going on with the subtraction yet. Okay, so we have diapers that we're looking at, and we have the two probability distributions for the random variables of x and y, and their means were already calculated. And I do have a typo. This adds up to more than 1, so I don't know where I made a mistake, but I haven't looked at the original data to see what I accidentally mistyped, so I apologize that those do not add up to 1. But we're going to do this anyways because I want to practice it. All right, so find and interpret the mean of t. T is where you're adding the two probability distributions. So I don't want to take the time to actually add them and then find the new probabilities. So what I'm going to do is remember the rule that we just learned, that if you have both means and you're adding the probability distribution, all you got to do is add the means. Addition works great with means. So if we have many, many selected days, the average total number of diapers used would be about 10.4 diapers. Okay, calculate, interpret the standard deviation. Well, I don't want to combine these and then put them in my calculator. And so I'm just going to look at the standard deviation. But I'm going to remember I never ever add or subtract standard deviation. Only multiplication works with standard deviation. So I'm going to take the variance. So I'm going to do 1.043 squared plus 0.768 squared, and then I'll take the square root, and I'll get 1.295. So the total number of diapers used each day typically varies by about 1.295 diapers from the mean of 10.4. Okay, all right, and so this last one down here, we have this girl that wears small diapers that are a little bit cheaper and the other girl that wears the bigger diapers that are a little bit more expensive. So we want to find the mean and standard deviation of the total cost. So we're going to add and multiply in this one, right? So we're going to do 5.5 times 0.238. So that mean times the price plus, and we can do this, right? We can add, we can multiply, plus 4.9 times the cost of those diapers. And that'll give me $2.77 per day. Okay, now the standard deviation, be careful. We're adding, so you cannot add standard deviation, but you can add variance. So we're going to take our standard deviation, multiply it by the price, right? So we can find the typical cost. But we don't want the standard deviation of the cost. We want the variance of the cost. Because you can only, 7, 6, 8. Remember, these are the standard deviations. Times 0.2975. We don't want the standard deviation of the cost. And remember, we can multiply standard deviation, so that's why it's okay. But we don't want the standard deviation, the new standard deviation, expanded one with the cost. We want the variance. So we add those. And I think, I didn't write this one down, but I think it was 34 cents. Okay. All right, so wrapping this up, what effect do math operations have on random variables? They're measures of center, shape, and variability. Remember, shape is not changed by adding, subtracting, multiplying, dividing. A center is affected by addition and subtraction, multiplication, division, but spread is only affected by multiplying and dividing. All right, what do we know about combining random variables? Well, if you are asked to add two random variables, probability distributions, then simply add their means, and you don't have to go through all that work. If you're asked to subtract, same principle, just subtract them, and you're good to go. Standard deviation, on the other hand, is a little bit more tricky, right? You cannot add standard deviation, but you can add the variance. And what if you're asked to subtract? Well, do not ever add or subtract standard deviation, but even though we're subtracting, the spread does not go away. Okay, how spread out the data is does not leave, so we need to still add our variances even though we're subtracting. Okay, so suppose that a certain variety of apples have weights that follow a normal distribution with a mean of 9 ounces and a standard deviation of 1.5 ounces. If bags of apples are filled by randomly selecting 12 apples, what is the probability that the sum of the weights of the 12 apples is less than 100 ounces? All right, so this is a lot of stuff in one question. But we are going to add up 12 apples, right? And we can, so it's like we're taking the random distribution, the random variable, would be all the apples in one bag, all the apples in the other, right? So we have 12 bags, but we know that the mean of our apples is 9, right? And so we just learned that we can add means. So we're going to add 9 12 times, 12 times 9, okay? So we're going to go ahead and do that, and we're going to get our new weight of 108 ounces, right? So that will be the mean of the bag, we're going to call it, which is adding up all 12 apples. Now remember, we expect the apples to weigh 9 ounces, so that's why we're adding up those 9 ounces. Okay, now remember with standard deviation though, we cannot add standard deviation. So what we're going to have to do, the standard deviation for the bag will be 1.5 squared plus 1.5 squared, right? 12 times. And I haven't put this in my calculator, and I don't have a calculator nearby. So go ahead and put that into your calculator. All right, and so the last part of the problem, so after we find that standard deviation, what we're going to need to do is times it by 12, right? So the standard deviation for the bag itself, so I'm going to talk about this one more in class because we didn't quite finish it, and I will actually add it onto the next video, okay? So I will talk about this some more, but what is the probability that the sum of the weights of the 12 apples is less than 100 ounces? So we know that for each bag we expect it to weigh 108 ounces, and then we'll have our standard deviation, we'll put that there, and then we'll use the calculator to find is less than 100 ounces. We'll find that area under that curve. So we'll finish that up. This is kind of where we ended, and then the bell rang, so I'm going to stop there, and we'll